Hello, and welcome to Old School Coding. I am going to be building a series of modules in C99, using some old school coding techniques. And what I'm going to be building up over time, if all goes well, is a discrete event simulation of an old school processor. This is similar to a number of projects I worked on way back. And by old school, I mean late 80s, early 90s. Mainly, I was a part of a group that built new computers, and we were able to get a lot of our work done using simulations of the hardware so that when we finally got our hands on the chips, we could make our software work and get it to market. This is at Sun Microsystems. So I'm going to bring up all the techniques we used back then and do some development using them to show you what software engineering was like back at that time. I will be making use of the tools and techniques of that time, which means I'll be coding in C. And the easiest way to get close to what we intended, I will be coding in C99. C99 was a standard published in 1999, which recognized the existing common practice of the day, which means most of the things in C99 we'd been doing for 5 years or more. Some of them didn't get in the spec, even though we'd been doing it that way since the late 80s. C90 did a great job of locking down what C was. And if there was some C vendor that didn't do something, it didn't go in the spec. With C99, we had a better handle on it. So I'm using C99 to mirror my development environment from the mid-90s. Likewise, I'm using Emacs. I'm not using a really fancy IDE. I'm just using the bare editor with the normal compile tools. So you won't see me doing massive refactoring, changing module names and all of that. That kind of tool was not common back then, so I won't be doing that. You will see a lot of manual editing of things in the editor. For building, I'm not using CMake. I'm not using project files. I'm not using a project manager that goes inside an IDE. I'm using Make. Make has existed since the dawn of time. That would be 1974 for you folks that don't understand that that's when the world began. Basically, Make says, really simply, this thing needs to exist to be newer than those things, and if it isn't, run these commands. Really super simple. So if you need to build a program, you need its object files. You say, get the object files and do this command. If you need the object file, you need to get the source file. So you get the source file and you compile the object file. So Make starts out as a simple concept, and then you build a whole bunch of implicit rules that try to do things like, well, if the file ends in .c, we're going to have special rules to build a .o and so on. File name extensions under the Unix operating system were just a part of the text. And the programs that manipulated the files gave them meaning, but the operating system didn't care. So the meanings tended to be casual. There was, in fact, a program that would tell you what kind of a file you were looking at because you couldn't count on the extension. So with that in mind, simple coding in simple rules, in simple build system, in simple editor. And that will be the last time I ever call Emacs a simple editor. It differs from modern IDEs only in that I have not loaded up all of the Emacs Lisp that would turn Emacs into a modern IDE. So you can see my README file over on the right. I'm setting out basically the stick in the ground. So, character set. Back in the late 80s, early 90s, we had 7-bit ASCII. So, if you were an English-speaking person, probably in America, maybe in England, you basically thought that ASCII was perfectly fine. If you were anywhere else in the world, ASCII was something you swore at because it didn't have your diacriticals, it didn't have your accents, it didn't have your letters if your letters weren't the Latin alphabet. So the world was going many, many different directions in how do you support things outside ASCII. But most development used C, which used ASCII. So, we're mainly ASCII, but you'll notice there that I'm allowing UTF-8 encoding of Unicode. That's because the first 128 code points of Unicode are 7-bit ASCII. And anything else is just gravy. Well, I like gravy. I like frosting on my cake. I like, gravy on my potatoes. So I will be using Greek letters. So if I'm talking about a microsecond, I will use a mu. If I'm talking about delta time, I will be using a delta, and I may even use a tau for the time. We may at some point start making a distinction between T and tau because we're doing a simulator. We've got real wall clock time and we've got simulated time. And we may have to make that distinction. But however, T versus tau, we'll have to think about that carefully. They're hard to tell apart. Depending on your font, they may be impossible. I don't like that. So yeah, I'll be using Greek letters in comments and in documentation. In string literals, I may print microseconds. I am free with that because I find Greek letters to be as familiar as English letters. If you don't, I'm only going to be using a few of them. You should be able to get familiar with them fairly quickly, and I will limit how much I use them. I won't be writing anything in Greek because I don't recall my 3 years of Greek from high school. So, testing. Over the years, people have formalized ideas around testing. The basic idea is you have a bit of code that runs that makes sure that another bit of code is doing its job. That's a test. Or a bit of code that runs that verifies a piece of hardware is doing its job. That's also a test. Or a bit of code that runs, you get what I'm saying. A test is a test. And people started saying things like, well, you ought to test every unit of your code thoroughly. So people came up with this thing, unit tests, capitalized tests, and now there's people that have to have discussions around what is the definition of a unit test. And this bit of code I've written, which tests this incredibly interesting and important thing that needs testing, is it actually a unit test? And then you get into arguments about whether this code belongs in the unit test directory. And this is all useless discussion because this is a bit of code that needs to run. So the distinction I make with tests is I have some tests that I want to run every time I run the program. So the program starts up, I'm going to run some power on self tests to verify certain things about the system. Some programs don't have any. Some programs have nothing inside of them that needs a power on self test. That's fine. I am going to be generous with my testing, which means I will be providing power on self tests for things that maybe don't actually need them, but belt and suspenders. That's the first kind of test. It runs every time the program runs. Second kind of test is a test that must pass for a build system to succeed. So these might be external programs that might pick up one of your modules and run some tests on it, or they might be code inside the program executable itself, where once you've built the executable, you run the program, you say run your extended built-in self-tests. I call these BIST for built-in self-tests. These may take longer. Power on self-tests need to be very fast. I want my programs to start up and run and do their job and get out of the way. Okay. If I've got a CATA file, I don't want it to spend 30 seconds doing built-in self-tests on whether it can read files or not, followed by putting out a 50-line copyright message, followed by actually counting the file. I want it to do its job and get out of the way. So, post very fast. Built-in self-tests are allowed to run a little bit longer, but in order for our build cycle, basically edit, compile, run, debug the tests, edit more, that loop needs to be very fast. Boom, 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 boom. Which means the built-in self-tests we run as part of every build need to be fast. And I'm aiming at less than a couple of seconds for everything to run, which means any given module needs to be substantially faster than that. I can't use my entire built-in self-test timing budget to test that a priority queue is actually a priority queue. So now we come to the third set of tests. These are extended tests. These are tests that you run occasionally. The extreme example of this is an acceptance test, which might exercise the system over a weekend. If you are producing an embedded system, you probably have a couple of these, and you probably run them in parallel on dedicated hardware. But I digress. So extended testing is every few builds, once you've done a major change, you go back and you run the major thing. You want that longer test to run before you integrate it. So if you're working in a branch, you're working on a feature, you're running the built-in self-test, that's great. Before you integrate that branch back into the development line, where the other people on the project are going to use it, you run your extended tests. And these take longer. These verify very thoroughly that your code does what it's supposed to do, not just with the normal case headers. So let's say I'm converting Fahrenheit to centigrade, and I test it. My built-in self-test tests 0 degrees Fahrenheit and 100 degrees Fahrenheit and 69 degrees Fahrenheit and 212 degrees, a couple of things. My built-in self-test might just check a couple of spot checks, but the extended test might include some other things, like if I'm a real fool and I'm passing in a pointer, what if that pointer is pointing to garbage? So what if the input is negative 5,000 degrees? What do I do? What output do I give? What if the input is 1,000,000,000 degrees? What do I output? What do I do? Make sure that works. Actually, that kind of conversion, that's something that doesn't have a lot of extended testing. Anyway, so yeah, the extended testing, you would test it beyond its normal input span. So what does it do when the inputs are bogus? Because you can't count on people calling you with sane inputs. So what do you do if the inputs are insane? That's some of that you might test with built-in self-tests, but you would certainly verify it with the extended testing. Extended testing is also where you do benchmarking. So sometimes you'll want to run benchmarking after the test, sometimes not. Do things like, well, I'm running a real-time control loop. Let's crank this sucker up and run it for, say, 5 minutes of real wall clock time. And let's verify that during this time, no cycle took longer than it should have. Every cycle took a positive amount of time. You check your, whatever attributes of the performance you would want to check would be checked during this benchmarking area. And that's something that you run before this goes back into a shared branch somewhere. So we've got these levels of testing. Notice I did not use the words unit test or integration test because I don't want anybody to ever have to get into a discussion about whether a particular test is really a unit test. Because if you go read Kent Beck's book, just to head off that discussion, I'm going to do a quick Google search here. It's not showing up on the screen, but test-driven design Beck. Test-driven development by example by Kent Beck is the book that a lot of people will point at and say, oh gosh, this book defines what test-driven development is. And what I'm trying to do here is find out when it was published. So let's see, I've got references to it. When published. I don't want to buy the book. I want to find, okay, originally published in the year 2000. So if we're talking about the edit, test, fix cycles we were doing in the late 80s and early 90s, we are not talking about test-driven development in the very strict form that Kent Beck put forward. And furthermore, I would say that there are no silver bullets in software engineering. So anybody that lists a series of steps you need to follow to have a successful project, they're blowing smoke up you. Okay? They are being sunshine pumps. The fact is that successful projects will often follow most of those processes, but following those processes don't make you a successful project. That's cargo cult programming. So my hat's off to him. He made some good points. He's got a great process he's following there. It works most of the time. And I am using methods that predate all of that, so I will not be doing strict test-driven development. I don't think I've ever done strict test-driven development because nobody's got time to say, I'm making a small change. Let's write a test that fails if the change isn't made. Now let's make the change. Now let's make sure the test works. Nobody got time for that shit. Yeah. So, no unit tests, no integration tests, no test-driven development, no following of external formally defined processes that were defined well after this period. We're going to write code that tests the things that we say our code should do. This does two things. First of all, it assures that the code does what it's supposed to do. It shows what the caller needs to look like. So if I've got a piece of code that's a FIFO, I write a test that says it tests the FIFO. Now that test becomes the example code. I say, well, here's what you need to do to create it. Here's what you need to do to push something onto the FIFO. Here's what you do to read something from the FIFO. Here's how you find out that the FIFO is empty. It's your test code becomes your example code. And then later on, when somebody comes along and says, oh, I can make that FIFO highly performant, I can make it run 10 times as fast, and they do that, the test still has to pass. And if the test fails, you have to look at how it failed and say, well, is it failing because the code is too fast? That's actually a thing. Your test could have wired down, it takes this many microseconds, and suddenly you're 10 times faster. Does it fail because a edge condition that I was counting on in the test, if the test was counting on undefined behavior, maybe the optimization changes the undefined behavior. That's okay. Sometimes you fix the test. Tests have bugs too. So there's that. That covers the testing philosophy. Build tools. I am using a makefile. I'm using GNU Make, which has a few extensions from the Berkeley BSD 4.2 based Make that I am familiar with mostly and have come to hate over the years because there's crankiness to it. GNU Make fixes a lot of the crankiness. People who haven't used the original Berkeley Make in 40 years sometimes forget that it has weirdnesses. GNU Make's got its own weirdnesses, but I understand those. I've worked with those, so it was very fast for me to set things up. What we see here in my GNU Make file, you see it's in the screen behind my picture, is refined over many, many years. And I have simplified the heck out of it. Yes, this is the simplified version. I've simplified the heck out of it compared to what I actually use in my projects directory, which is much more complicated than this. If you've got a projects directory that has several dozen projects, some of those projects are libraries, some of those are programs, some of those are programs that contain multiple libraries within them. So the makefile structure for that gets pretty crazy, but it does start off with having a common rules file that everybody includes, and then a makefile that just says what to do here. Now, this particular project I am building, this is a fresh project in the C language. Let me move my picture down a little bit. I have imported a few selected things that I want to start with. Now, that's another thing. Most projects you write in C don't start from an empty directory. You start by clone to own from something simple. And here I have cloned a very simple support package, and that includes this makefile. I have a bunch of things I set up early on. I'm not going to go over this in detail. We're just going to use it. Just realized if I went over that in detail, we'd be here for several more hours. Anyway, we have a set of make rules that will build this program and run it. More importantly, when it runs it, it will capture the output and will compare the output to an expected output. Let's look in the log directory, and we'll build this difference file. So currently, we have basically a blank computer program here, and it has no output and nothing expected, and it's got a little bit of standard error, which gives me a benchmark for my RTC NS call. So what am I doing? What am I doing for support here? I've got a little bit of support code. This is mainly the code that I want in place so that I can write my testing. Okay, so this is all code in support of testing. Things like I want a notion of elapsed time within this simulation, so elapsed simulated time. So I have a data type called tau, which I am going to use to carry my elapsed simulation time. It's an integer. First of all, integers are fast. Second of all, integers are great for indexing into arrays. So in theory, I could have a tau where it incremented by 1 every cycle of simulation, and then elsewhere I could be gathering data into arrays indexed by tau, or indexed by tau over 1,000, or whatever it comes out to. So we've got that. We've got real-time clock. This is the real-time clock from the simulation host. So I can say things like, sample the real-time clock, or do some things, sample the real-time clock again, see how much time elapsed, because performance is a requirement. It does no good to get the correct answer if it takes 10 years to do it. So we are going to be monitoring performance of any bit of code that is performance critical. And by performance critical, I mean code where I worry that it might take too long. So if we have a fundamental service we are going to be providing, which is going to be called millions and millions of times over the course of the program, I want to verify that that thing is fast, and I want to notice if some change makes it take a lot longer. So RTC is part of our support code. Our support code also has format. In C, you have the ability to take a bunch of data and format it by a format string using a printf, print it out or sprintf it. But it's kind of cranky to get it into a dynamically allocated string. Let's say you've got an arbitrary linked output. Oh, this is something original C didn't handle well on its own because it's complicated. That just means you are expected to write that code yourself, probably in a library. So this is my library routine for handling long strings. So we are going to do a printf of a format string and a bunch of parameters into a dynamically allocated string, which is long enough to handle it so we don't overflow. So support for the RTCs is in support.c, and that's probably a bad idea because it should be in rtc.c. Yep, okay, so I have some cleanup work to do before we get started here. The actual RTC code needs to be over at RTC. I will do that right now. I can pick up those two functions, just move it over here into rtc.c. I'll put it at the top behind my picture. And I neglected to put a comment. When I went through and commented this code, I neglected to comment the code in support.c beyond one-liners. So RTC prec ns returns the precision of the real-time clock as hold on, pause. Sorry, important phone call I had to take. Okay, so we're going to return the precision of the real-time clock as advertised by the simulation host, by the host system, in integer nanoseconds. So if we were running on a super duper future machine where it was so fast that the real-time clock was returning precisions of a picosecond, and we're actually doing significant things in less than a nanosecond, this interface is going to require that I return a positive number of nanoseconds. We're going to see that requirement elsewhere. The idea of getting multiple interesting things done within a nanosecond isn't actually a thing. We will be seeing some operations that complete in less than a nanosecond on modern CPUs. Very, very simple operations. However, the time it takes to sample the real-time clock, call into the operating system, get the value of the clock out, that's going to take longer because typically modern operating systems do not give you a simple memory address you can read that reads the value out of the clock. In fact, of all the computers I've worked on, the only system that gave you a address that you could read from and it would give you the value of a hardware counter was the Sun 4600 series, and that's because I did the port of the operating system to it. And by damn, I gave you a way to map that into your address space so you could read the hardware elapsed time counter. And it's, well, yeah, that wasn't a very fast system by today's standards. It was fast by then standards. But yeah, that was the idea. Anyway, so because we are calling into the operating system here, we will typically see times on the order of 10 to 30 nanoseconds for that call. This is on a modern Windows system. So precision here is what the operating system claims, and Ubuntu 22 whatever is pretty consistently saying, I have a precision of 1 nanosecond. I'm not sure what the accuracy is. Remember, precision is not accuracy. Okay? But it is saying that it's not giving us a millisecond counter here. The second function is calling up the RTC itself, which says get time. We're using the monotonic clock out of Linux. So this is a clock that is guaranteed to always be advancing in the positive direction. It's not something that generally is changed or set. I haven't gone to great lengths to chase down a performance counter clock, I'm not using any thread. You can actually ask for a clock that gives you elapsed time processing this thread, and I think that's kind of an approximate thing. But clock monotonic gives us our elapsed time. These are especially useful if you're measuring elapsed times on the order of many milliseconds. Okay, so if I actually get a measurement that says 100 milliseconds elapsed from point A to point B, that's going to be a pretty good measurement. So we moved that. Now, where was I? Before I noticed that had to be moved, forgot to comment this, RTCNS, return the number of nanoseconds on the host system since some arbitrary 0 point, which may or may not be the Unix epoch. So, get time of day on POSIX systems, on Unix systems at least, Unix-like systems like Linux, tends to be number of seconds past the 0 GMT of January 1st, 1970. So that's the beginning of time for that Unix recognizes. I think clock monotonic starts out at 0 when you boot. I'll just leave this arbitrary 0 point. Subtract to the results of 2 calls to get elapsed time in nanoseconds. Okay. So the other thing we ought to document is that tau, I'm going to change the documentation here, is elapsed time in arbitrary units. I may be using the type tau to have counters that advance in some time unit other than nanoseconds. So if this is nanoseconds, with sufficient range to store a nanosecond elapsed time of days, weeks, years even. So I'm going to use just a vague description here in the header file. Now, many things that return tau are going to return a nanosecond. So the data type is tau, and the unit of measurement is separate from the data type. So we're not saying that all tau are nanoseconds. That's why I put ns in the name of the function rather than in the name of the data type. So I'm not going to go into detail on the rest of this, just accept that there is a benchmark function, there is a built-in self-test function, there is a post function. I tried to set those up for RTC as an example of what they are. So, accepting that we do not want to go over these things in detail, I'm going to back out right now before I do go over them in detail. Make clean. And over in another window, I'm going to start up my build scripting. So we're going to get automatic builds going in another window that automatically rebuild and produce logs. So now over here, if I say make logs, that will recover the logs from the most recent build. Currently, I'm not stashing away the compiler output if there are warnings or errors during the build, which means that when I save a file, I need to have an eye towards that. I didn't want to toss a whole bunch of files in the log. I've done this in the past, and what happens is it gets fairly difficult to parse through it. I'm thinking if I just store the standard error of the compile in the log directory and have logs output it, that actually would be useful, wouldn't it? So, new makefile.rules over on the right here. I'm going to add some log files. And the way I'm going to do that is when I compile this, I'm going to say $2 greater than log /$.stderr. So now when I do a build, it's going to take standard error of the compile line and send it out to a log file named after the program. Okay. And that's in my makefile.rules. Then in my makefile, logs runs this program called logs in the, runs a script. So I did that in the scripting directory. This is the kind of tuning and tweaking you do when you start a new C program. And we see here that I already have find log directory, ignore empty files. -O says separate this, so we do this first one, and if that doesn't match, we do the second one. The second one includes all of this. Or if the name ends in stderr, then print it and cat it. So you see that I was doing this at one point, and I stopped doing it at one point, and I regret stopping doing it at that point. Now the thing is that this is now going to do them in some arbitrary order, and I believe I also, if I look over here, I may also have a stderr file being produced when I run my program. Yes, I do. So I want to do the run-stderr last. So we will do that. I'm going to break this into two find lines. So we're going to have cc-something or other.stderr and run-something.stderr as my two things. Go back to rules. Like that. So we have no errors from the programs, and we have standard error of the program itself. When I ran it, produced this one line that says each RTCNS call, if I do a ton of them in a row, then we're averaging 18.407 nanoseconds per call. This is over the course of, I don't know, I think I set it at a hundredth of a second, so 10 milliseconds or so. We have clocks coming back that are extremely high precision. As best I can tell, the actual accuracy of the clock is on the order of 20 or 30 microseconds, I want to say. Hard to tell. I'm not sure what the hardware counters are like in modern PCs, frankly, because on the systems where I worry about performance through my career, they've been embedded systems where you have a performance counter and it's very system specific, and you can observe that and you know exactly the props. If I'm running on a bog standard commercial off-the-shelf PC system, typically I'm not too worried about microsecond level performance with that precision. I'm more interested in, if I do it a bajillion times, how many milliseconds does it take? So I haven't worried about precision too much. So what if we actually have a error in a C file? So we have now taken our C errors. If we actually have a syntax error in our code, what does that look like? That's a syntax error. I'm going to save it. Now over on my terminal where I'm running the build system, it did cough up some stuff. And if I do make logs over here, now I get the errors from the most recent build. And this says unknown type. It's giving me an error right there. So I can now delete that. So I come back here and boom, there we go. Now that does mean that my log file is going to have a bunch of zero-length files in it. That's okay. You'll notice that I have some changes that I have built up, and I will be, the final version of this will become the first version pushed to the GitHub repository for this system. I'm going to start the main live coding project with what we end up at the end of this recording. So you'll notice that even though those standard error files exist in the logs, they aren't automatically being pulled into Git. So we are just fine here. Is there anything else I need to touch before I stop this recording? Verify that my actual microphone is good, my video is good. For the actual coding, I'm going to be moving my picture down to the corner and making it small like that, because you really don't need to see my face. In fact, I'm looking down to the right for that. I think for the live coding, I'm just going to turn off the video capture. You don't need to see my face, and it will confuse me that there are parts of my main screen that you can't see. So there we go. That's what that's going to look like for the live streams. I may turn on my picture if we actually get to chatting. If people show up on the live streams and they're chatting back and forth, I will throw my picture up on the screen so that they have a face to talk to. We can talk back and forth. I don't know how the YouTube chat channels are going to be reflected in the video at all. I think those just along the side. I don't think I need to put them in OBS or anything. I know a lot of streamers will use a tool that takes the chat channel and puts it on the screen somewhere just so it's part of the video. I may or may not do that. Anyway, so that's where we are. I think we are good to go. So at this point, I'm going to cut the recording, and the next step will be to come back live. I'm a little worried about my computer. We have some heating problems, and my power supply fan is going out. So new power supply coming in 2 days. I am a little worried that the sound of the computer fans is going to be coming through on the microphone. So bear with me for this recording And anything I do in the next couple of days until I get the new power supply in, if the fan is a problem, it will be fixed. Well, it'll be fixed whether it's a problem or not, but if it's a problem, bear in mind that it will be fixed. So I will see you in a live stream, I hope. Have a good one. Keep it safe.